Hello, hi. So I have started new playlist where I will discuss the design problem of related data structure and algorithm. So today I have picked the most interesting problem statement, which is mostly asked in interviews and we also use day-to-day life, which is the design the custom hash map, which is equivalent to the Java hash map. So concept of mostly related to any hash map, but I will follow the most of the approach and internal algorithm of Java inbuilt hash map. So let's jump into the problem statement first. So let me off my video and go to this problem statement. Okay, so statement is define and implement the generic hash map data structure from scratch without using any inbuilt map or dictionary implementation, and it should support the efficient key value storage and retrieval while handling the collisions and resizing. So overall, this problem statement uh, is similar to the inbuilt hash map, where the functional requirement is also given, like we need to support the put, get, remove, contain key, all four operation in on average time complex constant time complexity. And fifth point is we need to take care of a special handling of null value, null mm, as a value of the multiple entries, and also it should only support null, only one null key. Okay, so and non-functional requirement is state that like it should automatically resize, means expand when the number of entries exceeded the configurable load factor. Okay, so similarly, it should shrink also when the utilization drop the below the configurable threshold, means most of the space of the hash map is empty. uh, so in that case we should need to uh, it should automatically shrink. And scalability point is saying that like design the should follow the should continue to provide the near on average constant performance under the increasing load. So that's the point. So I will jump into the approach, and in this problem statement, I will follow the separate chaining strategy of the collisions handlings. There are multiple strategy to solve the collision. Like one is separate chaining, the second is open addressing. We will not jumping into that uh, different strategy. I will walk through only related to the uh, used one, which is the separate chaining strategy. So it's simple and mostly used. So for simplicity, I have taken the capacity 4 of the bucket to explain the uh, problem statement. So I have defined the four I have draw the bucket to visualize the better. So it's have a four size of capacity, and where we have indicated the entry E0 means all the entries with the zero index, and even with all the entries with the one index, similarly others. So these entry represent the object who is having the key value and some extra uh, information, and each entry also have like uh, address of next entries, so which is contain the next pointer. And for a given key, we need to as it's a generic, right? So it can be key can be any value, like int, string, any immutable value, any immutable object. So we need to first calculate the hash value. So we need to we would have some hash function which will give the hash value for the given key, which could be any 32-bit integer, right? So this should be, and as of now, like we have defined the max size of the, we have defined the capacity. So it should be mapped to any index of that bucket. So we have to do modulo of this caps. This has value with the capacity. So we'd give the any index number between the 0 and capacity -1, right? So, but this is modulo operation and it is expensive. And for any of the four operation like get, put, delete, and contains key for a given key, we need to calculate that the highest index. Okay, so it will be get add up, and it and this is the like expensive. So can we do optimize? Can we do better? So this part can be do better if we enforce the capacity of the hash map should be the power of 2. So this is the where we can replace the modulo with the uh, modulo with the bitwise AND operation. So let's see how. For a like let's suppose capacity is 4, right? So which bit representation is 100, and for a let's say key is equal to 3 and weight bit represented to 1 1. If I do the 1 1 bitwise and with the capacity -1 for any key which is power up to, if I do -1 that capacity value, it give the all the bit set. Okay, right? Suppose all the bits set, so we can do the AND operation. So we get the same value which I could get the same by doing the modulo operator, but it is, and reason behind it, reason choosing the bitwise AND operation, it is much faster than the modulo operator. The modulo operator is like we are basically performing the division operator, right? Internally. And in bitwise AND, why it is faster? Because it takes single CPU instruction. So that why it is faster. So as I said, I will follow most of the things of Java internal hash map uh, concept and approach. So I will choose the default capacity 16 and the load factor is 0.75. So reason behind default capacity I choose 16. One of these like it's also uh, is also used by the Java internal hash map. And second is why it's because it is the lowest power up to, it is the lowest power up to which spread the bits better and while uh, minimizing the memory wasted, right? So that's the, you can choose any number of any number which could be, but which should be the power up to instead of 16, but I have chosen 16 one. Okay, for the simplicity. And also I have chosen the load factor default value is 0.75. So load factor is like this is the decide the trades off between the space and time, right? So if we choose load factor 1, it should be load factor value should be 0 to 1, between the 0 to 1. So if we choose 1, at most 1, right? So lookup will be degrade. How lookup will be degrade? Because it linked list for any bucket index will be large and memory utilization in this case will be maximum. We are utilizing the memory at maximum possible, but we are degrading the lookup. If we choose the 0.5 half value, then it will be going, we are going we will doing aggressively resizing. Also we will be wasting most of the spaces. So for right balance and validated sweet spot is 0.75. So okay, so let's uh, jump into the code where I will explain uh, line by line. Okay, so I have already written the entire implementation, because if I write here from line by line, then it will take time. So I have written uh, so I will explain each line of the code and logic. So as I have explained, I have earlier discussed. So I have taken the entry as a inner class of this HashMap. I have taken a key, define a generic class HashMap, my HashMap, which is custom HashMap. Uh, I have make it static inner class. Reason behind it, uh, so it reduce the memory overhead. If it not static, take it will store the reference backward reference of this HashMap. There will be memory wastage. So I will, to avoid this, I will make it static. So this is the key and this is the value and this is the uh, hash value of this entry, means this the, and next is the next pointer, which is the stored address of the next entry to that linked list. And so uh, this is the inner class, and I have defined the default capacity 16, which is I have already discussed, and default load factor 3.75. I have taken the bucket of the entry size, capacity, and load factor. So I have defined the two constructor. Okay, one is the default one, where for the reason when user don't pass the default capacity, its own capacity and default factor. If user pass the its capacity and load factor, then we will map to the nearest uh, power of 2 to that capacity to enforce the capacity should be as a power of 2. Okay, so we will and then we will define the bucket, initialize the bucket. Next is method is the calculating the next power of the capacity, which is the simpler one logic. And second is the hash function. Hash for a given key object, we need to calculate the hash value, which is the integer value. And if key is null, handling the key as a null, then just return the 0. We will map to the 0th handle. Okay. For any other key object, we just use the Java internal hash code, which give the integer, any 32-bit integer. And this is the concept which I have explained, I need to explain, right? This is a new one. So instead of just returning direct hash value and get the index value by the doing this AND operation, we have do this. The reason is to do this to spread the uh, the upper 16 bit into like mix with the lower 16 bit. Like suppose, let's take an example to understand, to explain better. So suppose h1 for a given key, suppose let's say for key 1 we get the h1, and h1 is like 8. Okay, p2 we get the h2, which is, let's suppose, 20. I'm just taking one example to explain that, to explain this logic, why I am doing this. Okay, this 20. Okay, this one. So this is to avoid the collisions, to spread the upper 16 bit. into lower 16 bit, means we are mixing upper 16 bit to the lower 16 bit. As a 32-bit integer, we divided the 32 by 2, so which is 16. Half of the bit of upper bit we are mixing with the lower to avoid the collisions. So if we are not suppose we if we are not doing this, and let's suppose capacity capacity is 4. Okay, capacity is 4, then bucket index, and this bucket index we are doing. Okay, this will give all these key 1 and key 2, uh, key 2 and key 3. Key 3 will get uh, 0th index bucket. Okay, let me just comment it. 0th get. Why? Because 8, 4, 12 all is divisible by the 4. If we take capacity 4 for simplicity, uh, divisible by 4 get index 4. So they will get collides. And so instead of doing this, suppose if I mixing it 8, which is represented this one, if I mix with the 100, and let me divide with the first half bit, which is 2. If I do this, this will return the 1, means 2. So if I'm mixing this, and similarly 12, similarly 20, 12 is like 1, right? And 20 is like something. Let me just wait it. So let's suppose this is right. This is 20, and this is this one. This what with this will give. This will give the 15, right? 15 and 17. This will give the 15, and this will give the 17. So after mixing it, each will get the this value, and after doing this, this will give the second index, and this will give the uh, third index, right? This will give the first index. So all will get the different index. So collision avoided. So that's why we are doing this. Okay, that's the part. So second is put operation. I will explain later this equal operation. This is nothing but we are comparing two keys. Okay, so input operation, first we will calculate the hash value of that key, then we will get the index of the bucket. For that index we have the linked list. For we need to iterate from head to the tail. If any existing entries key matches with the uh, new key, then we will just update the value and return from here. Otherwise we need to create a new entry and append to the head of the linked list and update the bucket linked list, and also update the size. So I have discussed like in problem statement there is a threshold limit, right? For resizing, threshold is the capacity into the load factor. When the uh, hash map when the size of the when the total entry in the hash map is the exceeded the 75% of the capacity, then we need to the resize. We will double the size. and uh, we will just copy all the entries from the older bucket to the new bucket at new index. Okay, so similarly we will get the we have defined the get method which is similar to the put one, but we just need to check if value matches, we just return the value. So this is the special case when we are storing the null value for a given key. So to avoid this function return the false for a null value, we are special especially handle this case. So in case of value is null, we just returning a string in as a null so that it will get return the true. Remove method is also same as it is. First we will get the index calculation, and then for that index we have the uh, linked list. We need to just remove the entries which key matches to the given key, and we need to resize, decrease the size. Similarly for shrink logic, if size of the hash map is uh, 1/4 of the capacity, also is greater than the default capacity. This is the threshold one, like most of the space of the hash map is empty, so we should freed up. So that's why we are shrinking it. And resizing logic is simple. We are defining the new bucket entry, and for all old uh, entries need to need to iterate all the bucket one by one, and for each bucket list we need to map map its entry to the new bucket index, and at the end we need to just uh, update the current bucket with the new bucket, reference of the bucket to the new bucket. So this is the uh, implementation of the custom hash map. I will attach this solutions and problem statement in the video descriptions. You can walk through it. I will suggest first you will try to solve by yourself,